Today, we're going to finish discussing the idea about electric flux, right? Then we're going to introduce Gauss's law, all right? And the example. So that's the scope of today's class. And so let's first, let me remind what we introduced in the previous class. What is the idea of the electric flux in simple words? If you have certain surface which is exposed to the electric field, we can introduce what is called electric flux, and the meaning of that basically number of electric field lines crossing this or that surface, right? Okay, so now we started with the simplest possible situation. When you have uniform electric field and flat surface. So we discussed that in the previous class, and we introduced this formula. It's a dot product or scalar product between the electric field and the area vector. Right. And we've practiced already this in our recitation classes. Some of you will practice it today. Okay, so that was in the previous class, and now we basically finished at this clicker question. And actually, I want to poll it. I will give you just a half a minute. It should be enough, right? And the poll is in the chat, right? You haven't posted lots of messages, so you don't have to scroll up much. All right, so what do we have here? We have uniform electric field. Electric field strength is given, 100 newtons per coulomb. Then there is a flat surface tilted relative to the horizontal line, and the angle, this angle is 20 degrees. Surface 2 by 2. What's the flux, electric flux through this surface? Okay, quickly answer it. I will look at your answers, the distribution of your answers. All right. Although yesterday, okay, on Tuesday we almost discussed this question, but I still want to poll this. Right. Okay, so it should be enough. And now let me just quickly discuss, because here there is a very important point. Again, it's a flat surface, uniform field, so we can use the same formula, right? E dot A. So E A cosine of angle between these two vectors, right? And so electric field strength you can see. Area also for square meters. The question is which angle we should use, right? Okay, so now, of course, we need to show on the picture electric field vector and the area vector in order to see the correct angle, right? So, okay, let me open it up here. So, area vector must be perpendicular. I point it that way. Electric field, I just grabbed one of those lines and moved the tail of this vector, of electric field vector, to the tail of the area vector, because that's the procedure that you should follow to find the correct angle. The tails of both vectors must be at the same point. So as a result, the correct angle must be this one. Why is it 70 degrees? Because if I draw an auxiliary line which lies in this surface, right? So this line is parallel to that line. And as a result, this angle 20 degrees and this angle, they're the same. So this is 20 degrees. And this angle with that angle, they complement each other to 90 degrees. So if this angle is 20, then that angle, the correct one, must be 70 degrees. So that 70 degrees angle must be used in this formula, right? So we will have here 400 and cosine of 70 degrees, right? There is no special unit of the electric flux. When we actually move to the magnetic flux in a couple of months, there will be special unit for the magnetic flux. Again, speaking about discrimination in terms of units. All right, guys, keep your mics off. Somebody's mic is on and right. Okay, sometimes it's difficult to immediately see which one, right? Okay, so now let's make the situation more complicated. So up to this point we were discussing flat surface, uniform electric field. Now let's assume that surface is not flat and field is not uniform, right? We're just moving to the final tool, which will be used in the Gauss's law. You remember, we are preparing ourselves for the Gauss's law. So field is not uniform, surface is not flat. Okay, picture I took from the book. You see the surface, a curved surface, not flat. And again, it is exposed to a field which is not uniform. So how can we find the net electric flux through this surface? Typical procedure to set up an integral. You need to slice this surface in two directions, you see, this way and then that way. And then you just need to take infinitesimally small patch. Basically, very, very, very small, smaller than anything you can think of. And now I can make two statements about that small patch. First of all, since that patch is so small on this surface, I can say that that patch is essentially flat. With a very good approximation, it's essentially flat. Justification of that. Here I am standing in this small room, right? And since this room is so small relative to, is very small relative to the size of the surface, so with a very good approximation, I can tell it's flat. But of course, if I tell that statement to people from the International Space Station, of course, they will laugh at me, you're a stupid instructor, right? It cannot be a flat because you are on the spherical Earth, right? But because my room is very, very small relative to the size of the Earth, still with a very good approximation, I can treat it as being flat. Right? Of course, my neighbor's room will be also flat but slightly tilted to mine. Then neighbors of my neighbors, again, it will be flat but slightly tilted to there. So pretty much that's how we can model the whole surface of the sphere. Small, flat patches, right? So with a very good approximation, we can treat it as a flat. Then second statement. Since it's so small, I can say this surface, this area is so small, that patch is so small, I can say that the electric field is almost uniform. So again, how can I justify that? Using the same example of my room. So you know that the gravitational field changes from point to point. So force of gravity on the poles and, for example, on the equator, they're different. So gravitational field changes, right? But again, since my room is so small, even if you bring the best possible equipment, you will never be able to see the difference in the field of gravity between measured in that corner or that corner. It will be exactly the same. So with a very, very good approximation, I can say so that field of gravity here is uniform. So the same I can say about the electric field on that small patch. So it's so darn small. So we can say electric field is essentially uniform. So we have that patch being flat, electric field is uniform, so we can use the result from the previous slides, right? So we can use that dot product of electric field and the area vector, right? So now, as a result, I can write the flux, of course, which will be small, flux through this small patch equals electric field at that patch dotted with the area vector of that small patch. All right. Okay, so and of course then what? So that's a small contribution from that patch, but of course at the same time I can take the patch next to this one. There will be another small contribution to the total flux. I will have to add those two values. Then next patch, again, there will be small contribution. I have to add that contribution to the previous two, and so on. So I'll have to keep moving, counting all those small fluxes until I cover the whole surface, this curved surface. And again, you remember that procedure of adding small contributions? That's the integration. Integration is just a fancy word for adding small contributions to some quantity. So as a result, if we want to write the expression for the total flux through this curved surface, it will be like this, integral. The total flux through this whole surface equals integral of E dot dA. Looks nice, right? But strictly speaking, this integral is far from being trivial, right? It's calculus 3, and most of you did not take calculus 3 yet. So of course, at some point you will take it, and you will learn how to deal with surface integrals, with volume integrals and so on, right? But the beauty of this course, so we're going to use this fancy integration, but we actually are not going to take them. You will see in the example today, I will show that how we're going to use high school knowledge to evaluate eventually all these complicated integrals. All right, so that's why it looks scary. All right, but you will see that we will be able to take them without actually taking them. But of course, every step will be justified. Right. Okay, so now the last step, making situation more and more complicated. So here we calculated the flux through this surface, which is called an open surface. But there are also closed surface. Usually I ask students, so do you know the difference between open and closed surface? And so far no one could answer. Yeah, at some point you will learn this. In my case, I remember it was in analytical geometry. Okay, let me give you explanation, the difference between open and closed surface. So I have this piece of paper, right? So this piece of paper has two sides, this side and that side, right? Okay, so now if I start walking on one side, here for example, so I can easily get to the other side. And now I'm on this side of the surface, and now I can walk here. So because this surface is open, so I can walk on this side, and then I can easily get to that side of this surface. But what about surface like this? Again, you remember from the previous class, my Boston Marathon mug, right? So again, this surface has two sides also. Has inner side, right, and outer side surface. And now the cover is closed, right? So now if I start walking on this side, on this surface, side of the surface, if I try to get in or on to the other side, I will never be able, right? Unless you crush this surface, break this surface. Only in that case, I can get to the inner side, right? So this is an example of a closed surface. The previous example was an example of an open surface, and this is an example of a closed one. In simple words, without using some fancy terms. Okay, so now we need to write an expression. How can we find electric flux, the electric flux through the closed surface? All right. Okay, so now we have a non-uniform electric field, and now the surface is closed. For example, like this, I don't know, ellipsoid, or the shape of a American football ball, right? Okay. And now it's time, and of course, yeah, it's exposed to electric field, which is not uniform. But now, you see, I posted that when we introduce the area vector, and we had surfaces like this, I told you that you had freedom to choose direction of the area vector the way you want, right? You can point at it this way or that way. You had that freedom. And now it's time to take that freedom away from you. No more freedom, guys, right? So now we have to impose a convention. So whenever you deal with the closed surface like this, right? By convention, the area vector must point towards the outside, sort of like this. Why we're taking that freedom away from you, right? I'm practicing my dictatorship skills, right? Towards the outside, because now this result, the result of this slide, will be used in the Gauss's law. Gauss's law is the fundamental law, fundamental equation, and any ambiguities, and it shouldn't have any ambiguities. It's a fundamental stuff. And giving you a freedom that you can pick direction of the area vector this way or that way. No, it shouldn't be. It will be confusing. It will create a mess. Any fundamental equation shouldn't have any ambiguities. So that's why mathematicians, physicists decided to impose this restriction and convention. Area vector must point towards the outside. Right? Okay, I think I justified that. Right? And as a result, so basically, the procedure of setting up the integral will be exactly the same like in the previous slide. You need to slide this surface into small patches, and again, take one patch, calculate the flux, then the second patch, calculate the flux, add those fluxes up, and so on, and keep moving until you cover the whole surface. And now the difference between the previous expression and this expression, only in this small circle in the middle of this integral, in the sign of the integration. So that small circle means that integration is done over a closed surface. Basically, the fact that we're dealing with the closed surface is in this small circle in the middle of the integral. In a month or so, we will introduce another fundamental law where integration will be done over a closed loop. And there again, there will be a small circle in the sign of the integral, showing that will be a closed loop. But here, it's a closed surface. All right. Again, in calculus 3, you will deal with these circles in the middle of the integral a lot. Right. Okay, so that's what we needed. That's why we spent almost the whole previous class. We needed to prepare ourselves for the Gauss's law. We needed this expression. And now we are ready to state Gauss's law. Okay, so this is the number of electric field lines crossing this closed surface. And now we are ready to introduce Gauss's law. Enough about the flux, right? Now we know enough. But of course, we'll get back to fluxes when we will be in the world of magnetism. Right. Okay, so now let me move to the next. All right. So Gauss's law, it's a fundamental. I keep using this word fundamental, and there will be quite a few fundamental laws in this course, right? And what does it mean, fundamental? It means that you can apply that law at any point of the universe, at any moment of time, in any situation, and it must be correct. So far, no one could find any example where Gauss's law failed to work. That's why I keep saying it's a fundamental equation. And usually, these fundamental equations written based on observations. No one can derive them. It's like Newton's second law. No one can derive it. It just works because it works. It explains the world around us. That's why we use it. The same Gauss's law, the same law of gravity. No one can derive these equations. Of course, we can try to justify them, but that's the best we can do, right? So it means that what I can do in this case, I can say, "Tada! Here's the Gauss's law. Let's learn how to use it, right?" So no derivations. Okay, so pretty much on this level, I need to introduce Gauss's law. So let's assume that we have some arbitrary distribution of point charges, completely arbitrary. So you can make it more complicated, less complicated, it's up to you. Then let's take, for fun, a closed surface. Now you know the meaning of closed surface. So closed surface, of course, it's a two-dimensional picture. Looks like just a two-dimensional surface, but it's a three-dimensional, right? Since this surface will be used in the Gauss's law, we are going to call it the Gaussian surface. And after that, now we can present Gauss's law. Here it is. So this is the first equation in the set of Maxwell's equations, Gauss's law. And now, after discussion, since we spent quite some time discussing electric flux, now it shouldn't look scary for you. Because what do we have here on the left-hand side of this equation? It's just electric flux, which we just introduced, a few minutes ago. That's a number of electric field lines crossing this Gaussian surface which we picked. All right? And it is equal to the Q enclosed. It's a total charge inside of that Gaussian surface. You remember how I introduced in simple words what in the previous class Gauss's law? I compared it with Yankee swap. Right? You remember in the Yankee swap, you explore the surface of the box in order to predict the gift inside. And Gauss's law works in the same way. So you explore the electric field on the surface of this Gaussian surface, right? And then it allows you to predict the amount of charge inside of that Gaussian surface, right? So that's why I compare it with Yankee swap, Gauss's law, application of the Gauss's law. Right? So charge inside, electric field on the surface. Okay, so now properties of this Gauss's law. And of course, integration is done over this Gaussian surface. First, it can be applied for any surface your soul desire. Any, no restrictions. You can pick a very complicated shape, you can use simple shapes. I can even, for example, standing here, I can pick the Gaussian surface over here in my hands, right? And I can apply Gauss's law, right? Of course, electric flux will be zero, the total charge inside of my surface will be zero, so 0 equals to 0. It's useless, but it's correct, right? So no restrictions. You can apply, you can use any surface, closed surface, the key word closed. If your surface is not closed, it would be illegal to use Gauss's law, right? And we will be mathematical criminals and physical criminals, right? Okay, closed surface. Then, this Gaussian surface, it's a pure imagination. It's a pure mathematical concept. It doesn't mean that over here there must be some physical surface. No. You said, okay, you know what? I want to use this Gaussian surface, and it's your pure imagination. Right? So Gaussian surface, it's an imaginary one. Then, so again, let me remind you, so the meaning of this integral, right? So you take a small patch with the area dA, you draw area vector. Then, of course, there will be some electric field at that patch. So you dotted them to calculate flux through this small patch, right? Then you move to the next patch. Again, do the same, E dot dA. So there will be two numbers. You add them up. Then again, you move to the next patch. You will calculate small flux through that small patch. There will be another number. You will add that to the previous two. And so on. You will keep moving until you cover this whole Gaussian surface. And that's what we have on the left-hand side. Again, this is the idea of this integral. Right. Okay, so now that Q enclosed. In, it means enclosed, right? Inside of the Gaussian surface, right? It's the net charge within the Gaussian surface. Any charges outside, in this case like this, Q4 and Q5, they are outside of the borders. They are foreigners. We don't care about them. So we are not counting them. We only need to count charges inside. And of course, we need to keep track, or if that charge is positive, of course, it must go into this Q enclosed with plus. If it charge negative, of course, it must go with minus. So in this particular case, Q enclosed will be equal what? To, you see, Q1 is positive, Q3 is also positive, right? So both of those charges with plus, but Q2, since Q2 is negative, it goes into that equation with minus. So then the last piece, Distribution of those charges doesn't matter. It's very important. It simplifies calculations a lot. What does it mean? So it means that if you, for example, grab this charge Q3 and move it, for example, to this point, the right-hand side of the equation will be still exactly the same. Distribution of these charges within the Gaussian surface doesn't matter, right? As long as the charge as a charge inside of the Gaussian surface counted in towards that Q enclosed, that's it. So it's a nice, okay, so now we can state, okay, so now with these explanations, we can say now we stated Gauss's law, right? One of the fundamental laws in physics. So then I can say, what's most of the time, how do we use this Gauss's law? To find what? What do we want to know most of the time? And we use this Gauss's law. We want to find electric field. Electric field. So now we can use Gauss's law to find electric field. And also in the past we used Coulomb's law with a probe charge to find electric field. So now we have two ways of finding electric field. Both equally good, both equally strong, both doesn't have any restriction. Both don't have any restrictions, right? But of course, sometimes it's easier to use, for example, Coulomb's law. Like you remember, we integrated over a ring to find the net electric field in the previous class. Yeah, you can use either that, or now you can use Gauss's law. It depends on the situation. Sometimes this method is easier, sometimes this method is easier, right? So it depends. But of course, they're equally strong. Great, I can say now, so yeah, this Gauss's law looks elegant, maybe beautiful, right? You can use any adjectives you want. Where is the trouble? What is not wrong? What is not good about this law in terms of its application? In terms of its application. And the major trouble is here. Where is the electric field? Because most of the time we want to find the electric field. And the electric field is under the sign of integration. So if you want to find the electric field, you need to somehow extract that electric field from the sign of integration. The electric field is buried inside of the integral. And that extraction of the electric field from here can be a ridiculously complicated process. Yeah, it's universal law, it's elegant, it's beautiful, but if you try to apply this Gauss's law for some reasonably complicated system, it will be ridiculously complicated to do. Of course, you can use some numerical techniques. Now computers can allow you to do, but just from the mathematical point of view, it will be, oh my God, ridiculously complicated. Unless you have a nice distribution of charges. And that's what we're going to do in this course as the first application of this Gauss's law. All right. Okay, so that's what I just told you. And we're going to discuss actually we can discuss three types of symmetries, right? So let me move to the next slide. Spherical distribution of charges, that's what we're going to do now. So if you have, for example, sphere uniformly charged with uniformly charged or uniformly filled with charges, right? So application of the Gauss's law for this case is very, very easy. Then cylindrical symmetry. We're going to look at this symmetry in our recitation classes. We will find electric field outside, inside. So we have basically infinitely long, uniformly charged cylinder. And also, it can be easily applied to find electric field around an infinitely large, uniformly charged surface. So for these type of problems, application of a Gauss's law is very simple. Otherwise, if you have complicated distribution of charges, it can be ridiculously complicated. Right? Okay, so now after this, I need to switch to the whiteboard, and we need to start looking at the examples, because again, Gauss's law cannot be derived. We presented it, and now we just need to look how to apply it. Right? And guys, since it's one of the fundamental laws, right, and the first equation in a set of Maxwell's equations, a problem about Gauss's law will be definitely on the first midterm exam. I've been teaching this course for almost 7 years, right? And there was not a single semester where I didn't give students a problem about the Gauss's law on the first midterm exam. Usually it's either this symmetry or that symmetry. Okay? So now let me switch to the whiteboard, and I will start writing. So we have a sphere uniformly charged. And let's assume it's charged, positively charged. Right? So what do we know? The total charge in the sphere and the radius of that sphere. And the question is, we need to find electric field outside part A and inside of the sphere part B. Okay? So let's start with part A. Right? So we need to find electric field. Okay, I will write outside. So what does it mean outside? R small is larger or equal than R capital. Okay, as I told you like a couple of minutes ago, now we have two approaches that we can use to find electric field outside. You can either use Coulomb's law, like when we integrated to find electric field created by the ring, by a charged ring, right? You remember that procedure? Right. So we can apply it here, but the integration will be not simple, complicated, right? Second approach, we can use Gauss's law. And Gauss's law in this example is much easier. So let's try to use Gauss's law. Okay, first I will rewrite Gauss's law. So it's an integral over the closed surface E dot dA and equals to Q enclosed over epsilon naught. So that's our fundamental law, right? So we can frame it. And now, which step do we have to make first? Without that step, we wouldn't be able to move any further applying this law. Let me switch to your pictures. Okay, the first step, you have to pick a Gaussian surface. Because without that surface, you wouldn't, because here we must integrate over a surface. If you don't pick that Gaussian surface over which you're going to integrate, right? Then also Q enclosed, those are charges enclosed by your Gaussian surface. If you don't pick a Gaussian surface, you wouldn't know which charge are enclosed. So the first step must be, you have to pick a Gaussian surface, right? So then, and you remember, you have a freedom to pick any Gaussian surface you want, right? But before that, where should that Gaussian surface be? Of course, in the region where you want to find electric field. Because basically you use Gaussian surface to probe electric field. And if you're interested in the electric field outside, it would be silly to pick Gaussian surface inside of this sphere, right? So the Gaussian surface must be in the region where you want to find the electric field. So of course, here somewhere Gaussian surface must be outside. Then, about the shape. I told you that you have a freedom to pick any Gaussian surface your soul desires, right? Really any. Of course, you can, for example, pick very complicated, right? So a surface like this, right? And I will never be able to tell you that you are wrong. No, you will be all the time correct, because according to the Gauss's law, you should be able to pick any surface. And the Gauss's law would be correct. But the problem is, if you pick a complicated surface, you will never be able to find electric field. So what's the point of being correct if you cannot reach the goal, if you cannot solve the problem? So it means that you have to pick the best possible Gaussian surface so that you can use this symmetry of the problem, right? So you have to be smart. On top of being correct, you have to be smart and pick the best Gaussian surface. And in this case, the best one is a sphere, concentric with our physical, with the surface of the our sphere, right? Concentric, so the centers are the same. Okay, so let me pick it here. I will use dash line. So that's my Gaussian surface. Okay, of some arbitrary radius r small. And let me write, so this is a Gaussian surface. So now, once we pick the surface, now we can start evaluating the flux, electric flux, right? So I will probably write like this. So integral of this EdA. And now I want to see these vectors on my picture. I want to see electric field. I want to draw next to my Gaussian surface both of these vectors. Let's start with dA, right? You remember first, dA, it's an area vector. It must be perpendicular to the surface. Perpendicular, okay, it will be, so it means that since this is the sphere, so it will be radial. dA will be radial. Then the second, you remember convention that the area vector must point toward the outside, right? That convention, when I remove that freedom from you. So dA will be this. So if I take this small patch, dA that way, or if I take, for example, this small patch, so this will be my dA. Or if I take this small patch, right, so it will be dA. Okay, so now we know direction of dA. Now, electric field. Usually books say something like this. Because of the spherical symmetry, it's obvious that the electric field will be radial. Yeah, you can see that. Let me still justify that. Let me try to justify the fact that the electric field is radial. And I will do it here on this side of the board. All right. So let me justification that E is radial. Right. So I will do this. Let me redraw our sphere. It's not a Gaussian surface, it's this sphere, charged one, right? And let's say I want to find electric field direction at this point. Let me draw this dashed line. And of course, since it's uniformly charged, this sphere is uniformly charged, of course, let me take a small charge over here. Very small point charge, for example, over here, right? So this. Of course, this charge is going to create, is going to contribute to the net electric field at this point, and its contribution will be something like this. So this will be dE from this point charge. But since we have uniform distribution of charges, and of course similar charges will be everywhere in this sphere, of course I can find symmetrically positioned charge exactly the same in value over there. Symmetrical relative to this line, you see, connecting the center and the point in question. I can easily find that charge. There must be the similar charge over there. And let me draw contribution to the net electric field from this blue charge. So this will be contribution from that blue guy. So now let's add them up. Of course, you have to decompose along tangential direction and radial direction. And you see, tangential components will cancel each other. and only radial component will survive, will leave. So, of course, if you add them up, you will get, this will be net electric field. You see, only radial component leaves. Because for any charge on this side, I can find symmetrically positioned charge on that side, and tangential components will be cancelled. As a result, net electric field around the sphere must have only radial direction. All right. Okay, so now after this justification, I can also draw electric field vectors next to these area vectors. And you see, every time I draw them on the Gaussian surface, because here we integrate over the Gaussian surface. We're not moving away from that Gaussian surface. And these vectors on the Gaussian surface. Okay, so now I can draw, let's say this is my electric field. I can draw it also here, for example, electric field. Here, of course, you can draw as many as you want. I draw usually in a few spots. Okay, so now we can continue dealing with this integral once we finish drawing those vectors. So look, electric field and dA and the area vector, they perpendicular at any point on the Gaussian, parallel to each other. Sorry, why I said perpendicular. Parallel to each other. They are parallel to each other. So E is parallel to dA. So as a result, I can write explicitly this dot product. So it will be E dot dA. Of course, I can write it as E dA times cosine. Cosine of which angle? Two parallel vectors. The angle between them is 0 degrees. Cosine of 0 degrees, right? So as a result, cosine of 0 degrees is 1. And what's left? E dA. So that's my explanation box, right? E dA. So, okay, let me rewrite this integral. So it will be E times dA. So what's what we've achieved in this first step? Here we had vectors. Electric field vector, area vector. Now we have magnitude of electric field, strength, and dA, again, they are not vectors, they're just magnitude. So we no longer have vectors. That's the achievement of this first step. Now, let's use the symmetry. For example, let's assume that you are sitting over here at this point. And of course, this electric field, now I'm talking about strength of electric field. Electric field is created by what? Look, from this point, it's created by this distribution of charges. But now move yourself to this point. Of course, that electric field is created by this distribution of charges. But if you look from that point, that distribution of charges will be exactly the same as when you were there. Or you can move yourself to this point. And again, you can see if you look at the distribution of charges, it will be exactly the same. Exactly the same distribution of charges will be, it doesn't matter where you go. It means what? It means that electric field strength here, here, there, or at any other point on the Gaussian surface, electric field strength must be the same, just from the point of view of symmetry. Of course, vectors are not the same because you see direction of E here this way, here that way, here that way. Directions are different, but we no longer have directions. Here we have magnitudes only. We get rid of vectors. But magnitudes exactly the same at any point on the Gaussian surface. Of course, if you step away from the Gaussian surface, if you move here, of course, electric field will become weaker. If you move closer, of course, electric field becomes stronger. But since we are on the Gaussian surface in this integral, the electric field strength is the same. So I can open my second explanation box. E is constant, and I will add on the Gaussian surface. Sometimes students write uniform. No, it's not uniform. It's just constant at these particular points. on the Gaussian surface because we pick the best surface possible, so we can use symmetry. Electric field is constant on the Gaussian surface, so it means that we can extract this electric field from the sign of integration because it's constant. Any constant can be extracted from the sign of integration, from an integral, So I can write it electric field times integration over the closed surface dA. And it never happened before, right? So crash twice. Right? So it's the first time. So now it's still calculus 3 taking care of this integral. But anyone who is in this class can give you the value of this integral. So what's the value of this integral? Basically, we are adding a small area here plus small area plus small area plus. Here we're just adding okay, here, for example, I can use this ball, right? So dA plus dA plus dA plus dA plus. We keep adding these small areas until we cover the whole surface of the sphere. What's the answer at the end when you finished adding all these small areas of small patches? It's the area of the total sphere, this Gaussian surface. It's a 4 pi r small squared. So it will be equal to 4 pi r small squared. So you see how we handle this integral, which is far from being trivial from the calculus point of view. But here at this point, we just use the high school knowledge. Right? So, okay, so now let me write this line.
Wouldn't it be r cubed?
Huh? No.
Wouldn't it be r cubed?
No, guys, careful. It's a very, very common still. When I grade the exam, lots of students still confuses these formulas, right? So, cube, it's a volume of the sphere, 4 pi over 3 r to the power of 3. So that's the volume of the sphere. We're talking about the area of the sphere, 4 pi r squared. Guys, be careful because I see when I grade exams, plenty of students, okay, maybe like 10-15% making these mistakes. So write somewhere at the end of your notebooks those formulas, right? Because we're going to use them quite often. So E times 4 pi. We evaluated the flux, and next class we will take care of Q enclosed. Because now I just rewrote this Gauss's law. So we evaluated this integral, and then from the right-hand side, we can add Q enclosed over epsilon naught. Actually, in this case, Q enclosed, finding Q is enclosed is very simple. Some of you can see it immediately, right? So what will be Q enclosed? The total charge. Because the whole sphere, charge sphere, is embraced by our Gaussian surface. So the total charge Q, which is uniformly distributed over that sphere, is inside of the Gaussian sphere. So in this case, Q enclosed is just Q. Very, very simple. Right. Okay, guys. All right. Let's call it a day.